Then we say, how to make things go faster? Because we don't like things going slow. We want things to go fast. So there are two fundamental ways of increasing reaction rate. These two fundamental ways are increase the collision frequency and increase the proportion of successful collisions. So let's talk about collision frequency first, and then we'll go into successful collisions. So increasing collision frequency. So let's think about this logically. If you have a reaction and you want the reaction to occur, for the reaction to occur, we discussed that things need to collide, and they need to collide with sufficient energy in the right orientation. But the first rule in that essentially was they need to collide. If things don't collide, nothing happens. So we need things to collide more often. So let's think about ways we can make things collide more often. So let's just think about you've got air particles in a balloon and you want them to react and create something else, and those air particles within that balloon are bouncing around, because remember that we talked about our gas theory that we already talked about. Gases move in straight lines, so they'll go like bang, 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 bang. Yeah, that wasn't a straight line, but you know what I mean. Maybe it hit something there. Let's just say it hit something there and then went that way. But essentially, things go in straight lines. Let's go back to red. So things go in straight lines, and for things to continue, they continue bouncing around within a space. So let's think about that balloon and think about those air particles, and things are bouncing around in that space. So when things are bouncing around in that space, we want them to bump into each other more. We can't really manipulate how they're bouncing around, but we want them to knock into each other more. So how do we do that? Think about a couple of logical things. What can we do? We can speed up how quickly they're moving, because the quicker they're moving, the more likely they are to bump into each other, because, if they're following a set path and they're going to bump a certain amount of times, if it's really slow, then the reaction rate is slow. But if you make those particles move around quicker, they're going to bump into each other more. So let's speed up those particles. What's a way of speeding up particles? Heat something up. So first thing, increase the temperature. The higher the temperature, the faster we move things, the higher the collision frequency, the more fruitful collisions we get, because we're going to get more collisions, and even if the proportion isn't any better, you're still going to get more collisions, because overall you're going to get more fruitful collisions, because overall you've got more collisions. Then we think about a second one. I like to think of this as taking a metro train. So if you take a metro train at 11 o'clock at night, what's the likelihood you're going to rub shoulders with someone else? Pretty unlikely. You're probably even you're getting a seat, you're going to sit down, you're probably going to have even one of those 4 spaces to yourself. You're not going to have any issues getting a seat or rubbing into anyone. But let's say you take it at either 4 o'clock or maybe even after a footy match. What's going to happen? You're going to be squished up together, and you're bumping into each other all the time. You're bumping into people as you get on. You're going to be rubbing up against shoulders against people as you walk off and as you're standing there waiting for the train to get to your stop. That, if we think about it, is the same thing with particles. We push more particles into that balloon, what's going to happen? You're going to get more collisions. So how do we word that chemistry-wise? We increase the concentration. So increase the concentration or the pressure. So pressure for gases, concentration for solutes. So that's like aqueous solutions. And as you can see here, more particles, more collisions, etc. And then what's our sort of third one here? And this third one's a bit of an interesting one, because it kind of talks about solids. Or if we've got something bumping up against the solid for a reaction to occur, this is surface area. So one that comes up far less often, but if you've got more surface area on a solid, maybe that's the catalyst solid, or maybe it's part of the reaction, the solid, you need to have more surface area for things to bump into. So that is essentially our third option there. So we have 3 options there. The first 2 are the main 2. That third one's sort of just an extra one, but you do need to know it. So, increase the proportion of successful collisions. So we need to sort of give context to this as well. Let's just say overall we have, why does that keep zooming in? Stop zooming in. We have 50 collisions. That's how many we have. So we count the number of collisions between some particles in a balloon on, like a 1 minute period or 30-second period. You get 50 collisions. However, you only get products out of those collisions on maybe 20 of those occasions. Therefore, what you're operating at is a 40% collision rate. Now, what if we did something to increase those proportion of successful collisions? So what we would do is we keep this number the same. This number stays the same, but this number increases. And let's just say we went to like 35. So instead of having 40%, you're actually looking at more like 70% now. So you get far more successful collisions. You get more of the product that you want, or whatever is going to come out of it. So what are the two ways that we can do this? First way is, and I want to draw out this again, is to look at this. We're going to look at this in both examples, actually. This is our activation energy. Activation energy. So we have our activation energy here. Let's just say that 20 of those collisions could do this or greater. The other 20 collisions did this. The other 30 collisions did this. So they didn't have the activation energy. They got somewhat there, but they didn't get there enough. So then they just dropped. So what if we increase the temperature of everything that's in our balloon? Well, if we increase the temperature of everything that's in our balloon, we're going to increase the kinetic energy. And by increasing the kinetic energy, these ones are now going to be all the way up here, even though they don't need to be. And these ones are now going to be more up here. And some of them may still go there, but some of them may go just high enough to go there. So now what you've done is you've increased the number of particles that can actually go through what we're talking about. We can go through the collision, and we can successfully get a product. So increasing the proportion of successful collisions, what we do is we increase the temperature. By increasing the temperature, the particles move faster. They have more energy. So in the last one, we said, hey, they have particles move faster. You have a high collision frequency. In this one, we talk about how they have more energy. By having more energy, they can overcome that activation energy better. So then the key point is increasing temperature affects the rate in both ways. So it's the only one that will increase it in both ways, which is why it's the best way of increasing rate, is to increase temperature, because it has a twofold effect. It affects one and it affects the other, both parts. So higher temp, higher collision frequency. Then we have method 2, which is where we increase the proportion of successful collisions. And how we do that is we use a catalyst. So the first one was increasing the proportion via sort of just increasing everything. This one is by not increasing the energy of anything. It's in reducing the actual amount of energy that we need. So again, think of it, I keep doing this, and discard, apologies. What was that? Think about it like this. You have this graph again, and again, this was your activation energy. Now, again, same sort of thing, that green line was able to do it, the blue line wasn't. What if we said, all right, I put a catalyst in, and now the new line is this. As you can see, the activation energy has reduced. By reducing that activation energy, more particles are going to have sufficient energy to get through. So more of them are going to be able to do what we need to do. And so, essentially, what we get out of this is we get a higher proportion of successful collisions. So the way we describe it is like this. Catalysts provide an alternative reaction pathway with lower activation energy that allows more collisions to succeed. So really important how we word this. And this is one of those buzzwordy things you need to do in an exam or a SAC, and you need to be on top of this. Please do not word this as it lowers the activation energy. No. You need to say it provides an alternative reaction pathway with a lower activation energy. With a lower activation energy. You do not want to say it lowers the activation energy. It does, but it does not. It does not lower the activation energy of the path it was on. You cannot alter that path. But if you change the path slightly, you are then able to lower it because the new path you take has a lower activation energy. So, as you can see here, it says, catalysts provide an alternative reaction pathway. That is the most important thing. Once you have that, the rest of the answer should be fine. You need to have this in there. So if there's one thing you come out of today, it is that. Come out of today with it is that. So it's important, the alternative reaction pathway, catalysts change the reaction mechanism, so they change how it occurs. You don't need to worry about that in intricate detail because that is not 3-4 chemistry. All you need to know is that it changes how it occurs and the mechanism of it. So as you can see here, here's a really nice diagram of what I drew before, but in a much nicer context, one that you could essentially copy and paste into your sort of, if you're doing a summary book or you're doing, you have a workbook that you keep your notes in, this is sort of the diagram you reproduce or copy and paste it into there. So really important, that's kind of how it works. And you can see the different activation energies there. The delta H stays the same. The delta H does not change, and that's super duper important. So, as you can see, cool. So, we're going to go through some practice questions. Usually what I do is I give you time and go through it. Well, what I'm going to do with these now is I'm just going to go through them, so I'm not going to give you time. For those of you who are watching the recording and not watching the live premiere, you are welcome to hit the pause button right now and have a go at it. I would implore you to do that. I would implore those who are watching it to take a second and pause it and have a go at it. For those of you watching the live one, the premiere, you're not going to have the luxury of that, but that's okay because I'm just going to go through the answers with you, and I'm sure you have enough time to quickly work through them while I go through them if you just want to zone out quickly. But nonetheless, we have the oxidation of sulfur dioxide is an exothermic reaction. The reaction is catalyzed by vanadium, V oxide, and you've got this here. Which of the following energy profile represents both the catalyzed and uncatalyzed? So remember, when we have this, we start with the same energy, we end with the same energy. So this one is wrong. This one is also wrong. How do I know that? Because they don't start with the same energy and they don't end with the same energy. So, cool. Move on to B and D. It says it's an exothermic reaction. This is endo. So this is wrong. Process of elimination, I've only got B left. I look at it, B is actually, it's correct anyway. Process of elimination, I knew it was right before even looking at it, but B is correct there. We start at the same energy, we finish at the same energy, and the only thing that's different is the activation energy here. So, awesome. Moving on, so to summarize, these are the 5 major factors. You need to be really careful with these. You need to make sure you name them correctly. So you may be given a scenario, you need to make sure you name the right ones, and you really need to know sort of which ones apply to which. So obviously your reaction rate in terms of successful proportion of collisions, and then the other one was how many collisions you get. So then you're going to get more successful collisions naturally. So think about it, proportion and number are sort of the 2 different ones. So again, we have another practice question. Again, pause if you're at home, but I'm going to go through it. So what we have is bromomethane, CH3Br, is toxic, odorless, colorless gas. It's used by quarantine authorities to kill insect pests. The simplified reaction for the synthesis is you've got methanol, you've got HBr, and you end up with your bromomethane and water. And it is an exothermic reaction, and it is at 298. So the manufacturer investigates the reaction conditions, the time of the process, and takes the percentage yield. So this is actually what we're doing here, is leading us into our next topic. So this is sort of a little bit of a preface as to what we're about to go into. Predict the effect of change given below on the rate of the product of bromoethane and circle your prediction. So if we increase the temperature. So this sort of question here is very much what we would talk about with yield. And it's really going to talk about equilibria. But they've sneakily, very sneaky, they have produced a question here, and this is a VCAR question. I apologize, I put the thing in white, and I don't know why I did that. I will make sure to fix that up. Not sure why I made that white, so you're not going to be able to see which exam. I can't even remember what exam this one's from. I do apologize, I'll fix that up at the end. But essentially, where this sort of question is an equilibria question. It's not a rate question, it's a yield question. But they've very sneakily made it into a rate question. They've gone, hey, what is the rate? What is the rate of production? Usually this would talk about yield. This is a very typical yield question, but they've actually made it rate. So when we think about it, it says we're going to increase the temperature. So if we were talking about yield and you increase the temperature, you're actually going to go backwards, but we'll discuss that in a little bit. In this case here, what we're actually going to do is we're going to increase, because when we increase the temperature, what happens? It increases. Why does it increase? So your reason. So it's going to increase. So usually you would circle, but I'm just going to write it. And then why? So you would say that in very shorthand, I'm going to write temp. You would never write it like this, but this is what I'm going to write at. Kinetic energy, so of molecules. You would write out what those molecules are, but I'm just going to make shorthand this thing. So then you would say 1, there is increased collisions. And you would write 2, there is an increased proportion of successful collisions. I also apologize if you can just hear a whir, like a whir in the background. That's my laptop just struggling. It does this every time. There's no way around it. So this is what you would write out as a paragraph. You're not going to write it out in shorthand like I just wrote it out. You're going to go ahead and write this as a paragraph. This is what you need. So this is a 4-mark question, which I think is a little bit absurd. I would really only warrant this a 3-mark question, but 1 mark here, and then you're essentially, I would say this is a 2-mark question. There is 1 mark for stating the thing about your information about energy kinetic, and then there is 1 mark for giving these 2. In this question here, there is actually 1 mark for both the proportion of collisions and the total collisions. I think that's way too many marks. This is a 3-mark question now. This was a little bit of an older question because I think it was like 2012 or 2011. But essentially, this question now is only really worth 3 marks. They're not going to give this 4, but for the sake of it, that is where your 4 marks were for those of you who sort of paused and had a go. So then we have predict the effect of each change given below on the rate of production of bromomethane and circle your prediction. So what if we increase the pressure? So again, we've got the same one. What's going to happen when we increase pressure? Same thing, we've already talked about this. We're going to increase. Why is that? And this question here, you can only really give the 1. You can say, as there is a sort of a smaller space or an increased pressure, you have an increased movement, and you end up with an increased, number of collisions. And with that increased number of collisions, you get an increased number of successful collisions. So I very much short-handed these because I don't want to go through them in super detail and take up all your time. Successful collisions. But that is essentially how you go through a question like that. So